get started, and thanks for coming on to the first department semester seminar of the spring semester. And it's my pleasure to introduce a colleague and friend of mine who is now our newest affiliate faculty, also in atmospheric and oceanic sciences, Professor Paul Stoy. So those of you who are grad students and are looking for an external committee member or advisor or something, no bother him. But Paul's affiliation tenure home is in the Department of Biological Systems Engineering, which if you haven't been to, it's up on Henry Mall, just across the way. And then he's affiliate here in AOS. Paul just started here after moving from being faculty over at Montana State in what's the department? Environmental
Land Resources.
Land Resources. Okay. But this is not a new place for Paul. He actually did his undergraduate degree here in zoology, right? Which is now integrated biology. But spent quite a bit of time here in our department, collaborating with Chris Kasharik and John Foley and folks, and so has quite a bit of history with us. That must have been back in late 90s, early 2000s. And after that, went to Duke, right, to get a PhD with Gabi Katul, who's a micrometeorologist extraordinaire, and probably where we first met at some point somewhere, in some meeting. And then later on, after getting his PhD, did a postdoc in Edinburgh, right? That's nice. I'm doing this from memory, so. And then ended up in Montana and now here. So it's really great to have you here. So those of you who get to know Paul, you should also get to know Amy Trowbridge, who is his spouse and a faculty also new faculty in entomology, and also has lots of cool, interesting research that hopefully we'll get to hear more about. We heard last year CPEP, but also if you're interested in atmospheric chemistry and volatile organics. But today we're going to hear about recent trends in climate of the North American Great Plains, and leave it at that. Thanks.
Thanks so much. Thanks for coming. Thanks for this introduction. Most of this work was done by former atmospheric oceanic science undergraduate Gabe Bromley, who is a student in lab at Montana State. I really want to thank Gabe. Many of the slides that I'll be presenting are from Gabe or Tobias Gherkin. This is mostly a project funded by the National Science Foundation, although I really want to point out that what got this all started was some seed funding from the Montana Wheat and Barley Committee, working with actual farmers on real challenges about the hydrometeorology of the Great Plains. Data from a number of sources. Thanks also for the invitation and for Bailey for organizing. So what I do, because I want to introduce myself to the department a little bit, is I am very interested in the role of land management in the climate system. I'm fundamentally an ecosystem ecologist. My interest is in energy fluxes, first and foremost, but that means a lot of different things. So I'm interested in, as we decide how to change land management, okay, we differ the properties of the surface. Right? There's more or less albedo, solar radiation being reflected back out in space, changes in the amount of evaporation, evapotranspiration, changes in how energy is partitioned in the sensible heat flux, also fluxes of things like biogenic volatile organic compounds, which create secondary organic aerosols and perhaps eventually cause condensation nuclei, all of which impact the atmospheric boundary layer and cloud formation processes, which creates an interesting feedback. It's the amount of solar radiation that reaches the surface, temperature of the surface, precipitation processes, of course, all sorts of things. And if this sounds a lot like what Ankur works on, in fact, it's true. And so I did some mild archaeological investigations to find that our first collaboration was actually a paper published in 2006 by Faith Ann Heinz, where both of our sites, right, mine, Duke Forest, Willow Creek was one of the many that Ankur worked on, were some of those that really challenged the modus gross primary productivity products. Okay. Our sites didn't quite follow along the line of what they thought GPP should be, resulting in algorithmic improvements, resulting in hopefully an improved understanding of the global carbon cycle. So, less ancient history, more modern stuff, I want to talk about the Northern Plains. I want to talk to you guys about why we want to be interested in the Northern Plains. This is not a place where a lot of people live, yet I find it particularly interesting. It's changing quite dynamically. I'll I'll talk about how things have gotten moister. When you publish a paper on such things, what happens then is you have a severe drought. I'll talk about the mechanisms that underlie that drought. And the fact that it's a flash drought made it extra interesting for me to come back here to Wisconsin, where some of the world leaders in understanding flash drought, Jason Odkin, people in space sciences, are at the forefront of understanding what these very rapid drought events mean, and perhaps how to forecast them better. And now that I'm here, I've been thinking, of course, more and more back to my home state. I'm from Hudson, Wisconsin. This is up by St. Paul. But what are the implications of changes to the climate of the Northern Plains to Wisconsin, right? Of course, we're placed more often than not downwind of the Northern Plains. What I'm really talking about is kind of the decadal climatology of happy little convective clouds that sometimes can turn into big mesoscale convective systems, bringing things like floods. So, why the Northern Plains? When I was looking for material to teach my old course called Environmental Biophysics at Montana State, I ran across this figure showing changes in heat. Okay, apologies. Okay, this is from Climate Central, a very nice website. This happens to be in degrees Fahrenheit per decade, but this is the slide that got me thinking. Why is South Dakota not warming? Why might it even be cooling? What's happening in South Dakota? Not a lot of people ask these questions, but I'm going to argue that it's really important because it's not that far away from us, okay? And I'm giving a talk in Brookings on Friday at South Dakota State. So, other seasons are warming about as we expect. So right here in the epicenter of that warming is my hometown of Hudson, where we used to flood our backyard and play hockey in the wintertime, and now you'd be hard-pressed to do that. Where it is measurably and demonstrably different going back to the winter now than when I was a child. And temperatures have increased, but you see now, we're talking a slightly different period, maybe a different time scale. You see this large area of what we call most of the Northern Plains not warming, perhaps even cooling in the summertime. What's happening? So because this is funded by the National Science Foundation, we can get beyond that hard border that we often see along the northern fringe and ask, is this actually a small part of a large North American climate trend that warrants our investigation? Why? And this is the climatic research temperature trends, the near surface 2-year temperature trends, April, May, June. So slightly different from a typical, actually this is the typical climatological spring, where we see, in degrees Celsius per decade, perhaps a cooling trend. These stipplings indicate that it is significantly different from the 0.2 degrees Celsius per decade warming that the globe has otherwise seen from 1970 until 2015. And so this is what Gabe just published in this month's edition of Journal of Climate, is really a recent decadal climatology of this coupled United States and Canadian region. Right, we're defining this as the Canadian Prairie Province Ecozone plus Neon Domain 9, Northern Plains. We're bringing these two things together and finding, especially in the months of May and June, that's when things are really doing something quite different to the rest of the globe, where we have a cooling of near-surface air temperatures. We have a big decrease in the atmospheric vapor pressure deficit. This is an extremely important metric for crop growth because plant stomata respond very strongly to high levels of vapor pressure deficit. So we have more moisture in the air, at least as far as the plant will sense it. And then we have actually a lot more precipitation. Question, Dave?
Sorry, do you define vapor pressure deficit for?
Vapor pressure deficit. So it is the amount of, is the difference between saturation vapor and actual vapor in pressure units. And then precipitation, you see, okay, this is again in millimeters per decade, so about 4 decades. So we're getting in some cases close to 4 centimeters. It doesn't sound like a lot, but this is only 2 months of the year. And we know how much precipitation has increased in Wisconsin over the past few years. So we're seeing something happening across this entire region that I think is quite important. One of the big reasons why is that this extremely agricultural region is a critical global breadbasket. For wheat, okay, over here we have a lot of corn, soy, oilseeds, all sorts of crops are grown here, and things are surprisingly getting cooler. So you might ask, am I cherry picking these months of May and June and saying, oh, look at this, May and June are getting cooler, therefore the world isn't warming? That's not the case. A lot of the net carbon dioxide uptake is using eddy covariance measurements. This is a flux of carbon into the biosphere by month in a winter wheat crop and a spring wheat crop. You see that June is a key month for plant growth here. It gets really too dry once you get toward, August in the case of winter wheat, spring wheat still hanging on in July a bit. To sustain that growth, right, wheat wants to make big seeds and die, so it grows early on. And so during that period where the crop is taking on a lot of its carbon, climate is getting cooler. Question?
Paul, are those species really sensitive to the cooling, or do they not care?
This is a good question. They are rarely suffering from a lack of heat during June, but of course, right, if things get really kind of cold in April, May, the biggest threat oftentimes is the ability of farmers to put the crop in the ground. So that's, to me, the more important thing that's happening. And then hail damage is also extremely important, which I won't be talking about. So there's flip sides to every coin when it comes to understanding what's important here. So Montana is one of the biggest wheat producing states in the nation. The Canadian prairies are really a global wheat breadbasket, and that's why we're focusing on wheat, even though a very large mixture of crops is grown here. Although it's becoming kind of dominated by corn and soy land continues to move to the north and to the west. When we look at the probability distribution of air temperature trends in degrees Celsius per decade, this is the northern plains versus the world, we see that this little hump here is to a large degree comprised of the center of North America. We are cooling when the rest of the world is warming. What's happening? The Canadians for some time have been investigating this, right, because it's their prairies and it's our Dakotas. So they have found a decrease in summer maximum temperatures of about 1 degree Celsius. This gets very important for heat stress risk to crops. They've seen an increase in precipitation of 10 millimeters, so about a centimeter per decade. This sounds like peanuts, but we're also talking about parts of the world that might only get 12 inches of rain over the course of a year. These are very meaningful changes in precipitation, and my Canadian colleague says that farmers will kill for an extra rain event or two in some of these areas during the summer. In terms of radiative forcings, we see a negative 6 watts per meter squared negative forcing in the summertime in Canada. This has been characterized by a number of papers. Some of those are there. I'll be happy to give you the full references. Against an anthropogenic warming, just for reference, since the dawn of the Industrial Revolution, of about 2.5 watts per meter squared globally. So the Canadians have cooled their prairies by over twice as much as the globe has warmed just in the past few decades. The mechanism, and this is a figure from Gameta and others, 2007, so quite some time ago, is that when you have a condition of bare soil on the ground and it receives solar radiation, that energy is partitioned quite a lot into sensible heat, thermals, rather than latent heat from evapotranspiration, because there are no plants actively taking water through the vascular system, through the stomata, up into the air. When you have, and that results in a relatively high atmospheric boundary layer and a dry atmospheric boundary layer. So when you have vegetation, and these are not the right numbers, right? Our simulations suggest that in the northern plains, under vegetative conditions, you're probably going to get an atmospheric boundary layer of 1 to 2 kilometers. That number isn't that far off. When you have vegetation, you are partitioning your energy a lot more into latent heat, less so the thermals that rise. You have a shallower and moister atmospheric boundary layer. Why am I talking about bare soil? How can this possibly be important? What people used to do in Canada, and still do in the United States of America, is adopt a cropping system where they would plant wheat one year, and then the next year they'd leave their field fallow. And then they'd plant wheat, and then leave it fallow. And we're talking about big areas. We're talking about things the size of Saskatchewan. And once you think about how much land was in bare ground during the peak of fallow management, so in the late 60s, early 1970s, the difference between the amount of fallow that there used to be and the amount that there currently is the size of our fine state, excluding our ownership of Lake Michigan and Lake Superior. So that much land was brown during the summertime in the Great Plains, and this is actually great because fallow is not a sustainable land management practice. Okay. Soil erodes, there's a lot of wind erosion, we're only losing soil carbon due to respiratory processes, we're not planting something. Farmers went away from this fallow management strategy because they realized that they're farmers, they can make more money by actually putting something in the ground. And a lot of the theories for why people, or the reasons for why people used to use fallow, right, namely that it saved a little bit of moisture, didn't really hold up once alternate cropping systems, including really shallow-rooted cover crops, oilseeds, and other things, began to become more economically friendly. So, a happy circumstance resulted in this decline in bare ground. My argument is that it really also changed precipitation processes. Once you add up Canada plus the United States, the difference between the total amount of fallow that used to be around versus the amount now, okay, is on the order of the size of Arizona. So we're talking about big, big brown areas because, again, Saskatchewan is not a small place. And you can see still in the United States, there's a lot of fallow management that remains. Okay. Still about over 5,000 square kilometers, mostly in Montana and the area that is also in wheat farming in eastern Colorado and western Kansas. Those places still adopt wheat fallow rotations. I've been talking about Saskatchewan as the epicenter of bare ground loss over time. From the 1970s to the present, different agricultural statistics in the United States. But you see here, especially North Dakota, used to have a lot of fallow, and now nobody uses fallow anymore. Whereas Montana, here, Kansas, and to a lesser degree Colorado, still have a lot of bare ground in summer. There is a wonderful paper in Nature just a couple of years ago by a group from the University of Maryland that shows changes toward bare ground, away from bare ground, right towards different types of forests or fields. And there is this big swath across the northern part of the northern North American Great Plains where things have become very much greener over the past. In this case, this is from 1982 to 2016. And we're looking at bare ground changes per pixel on the order of 30%. So things are 30% greener now than they used to be. Over, again, you see our Wisconsin over here. Right. Let's map that thing up here, and now you see the scale of the challenge. So, we can measure all of these things. We can use eddy covariance over wheat fields, over fallow fields. Our producers tend to like driving their combines around our towers, right? So it didn't provide a huge hindrance to them going about their business, and see over the course of the vegetated growing season what dirt versus, or actually it's really just kind of dead plants, versus living plants means to surface fluxes. What we have here is a cumulative sum of evapotranspiration. Okay, this is of course related to latent heat flux. That's the energy that it takes to evaporate water. This is the amount of water here in millimeters. So when you start, let's say in April, and you're evaporating water, and if you have a crop, you evaporate a lot more. So there is a water savings element to fallow, and this is why farmers continue to use it. A little bit of water down in the deeper soil layers is a bit of an insurance policy to them against a dry year. So if they have deeper soil layers down below, and if they have a dry summer, they might be at a benefit later on, but this, again, right, it doesn't, it's in most areas not an economic advantage to do so, which is why fallow has gone away. When you add up the amount of heat flux, this is in cumulative megajoules per meter squared, and you have your crops. Okay, our winter wheat is going to really leaf out sooner than our spring wheat. You see almost no increase in sensible heat flux during this June and July period, with almost all energy is being allocated toward evapotranspiration, not even a lot of ground heat flux at these times. And you have the continual increase, of course, in sensible heat flux in our fallow fields, such that you have about 50% more heat entering the atmosphere under this bare ground condition. Why, again, is this important? When you have differences in the Bowen ratio, this is the sensible heat flux divided by the latent heat flux. it changes the height that the atmospheric boundary layer reaches, and it changes the level of the lifted condensation level. Sorry, the height of the lifted condensation level. And if you have a crossing between these two layers in the atmosphere, you might get a convective cloud. You also might not. But if they don't cross, that parcel there that reached the top of the atmospheric boundary layer wouldn't have a chance of making the convective cloud. So if you have conditions that are right for convection, you might get it. And we're using that kind of framework, rather than formally simulating these little clouds, discussing the likelihood that they may or may not exist over decadal timescales as a way of understanding how changes to the land surface have impacted convective precipitation processes in the Great Plains. So, first and foremost, have the fluxes even changed? We're using here, this is a paper 2018 in Journal of Hydrometeorology by Tobias Gherkin. MERA-2 data, this is our sensible heat flux. These different colors are different months of the year. 1980 is when that data set began until more or less the present. You see a decrease in the sensible heat flux, an increase during most months of the latent heat flux, such that our Bowen ratio has decreased from about 2 on average, regardless of month, surprisingly, to about 1. Okay. This isn't the best data product, but it's all that we had and is consistent with our understanding of how the land surface has changed in this part of northeastern Montana that has in fact seen relatively large land cover changes. That's right kind of in the centroid of what I'm defining as the Northern Great Plains.
Does MERA-2 include that land use change? Or is this just purely from the atmospheric temperature analysis?
My understanding is that this is merely from the atmospheric temperature. I don't, and this is, right, so this is Glasgow. It's a pretty remote part. It's actually the city that's furthest from any large city in the United States, excluding Alaska. Because it takes like 5 hours to get to the buildings. But, again, Glasgow is kind of where a lot of this research has been aimed at, because it's in the middle. But good question about the MERA-2. This is not my area of expertise, so I'm always willing to learn more about these sorts of things. There have also been very pronounced changes in the lapse rate, especially the moisture lapse rate. So if this is the lapse rate potential temperature and moisture, this lapse rate for moisture is getting more negative because there's more moisture at the surface, right, resulting in a more negative moisture lapse rate, at least over Glasgow. So these things are combining, and we want to put all of this inference together, including some eddy covariance data, to model the likelihood of changes in the atmospheric boundary layer lifted condensation level crossing as a necessary but not sufficient condition for convective precipitation. So when we do that, right, and we're using an approach after Milcray-Porperato, 2009, where we're taking the lapse rates of temperature and moisture, and then surface temperature and moisture, assuming a sinusoidal signal of net radiation, and that Bowen ratio is constant during the day, but you can model pretty effectively the change in atmospheric boundary layer height versus time is primarily a function of the sensible heat, of course, also the temperature lapse rate and other things. And you can see how high the atmospheric boundary layer gets and if it crosses the lifted condensation level. And there are 4 possible outcomes. Again, we're combining Tower, MERA-2, and other data to perform these, to get this inference, where you have a crossing, an atmospheric boundary layer height that gets above that of the lifted condensation level, such that a parcel layer that was lifted that high has the potential to create a cloud. You can have that happen and have rain. You can have that happen and not have rain. Every cloud doesn't have to rain. There are 2 other situations. Right? Here's one where you do not have a crossing and there is no rain. You can also not have a crossing and also, of course, get rain, because this is a model. Right? Models aren't true. And is all precipitation local? No, of course not. There could be a synoptic event. Right? There could be some other meteorological driver, like a mesoscale convective system or what have you, that brings rain events. So we validated this mixed layer model using data from GGW, that's Glasgow, Montana. And we find actually reasonable timing for this crossing between the atmospheric boundary layer and lifted condensation level and rain events. And in fact, kind of a simple rule of thumb. This is a slightly messy figure. I'll ask you to see through it for these means and standard deviations of when you have crossing, right, or situations when you have relative humidity at the surface of above 50%. So to first order, right, much of the time, if you have moisture at the surface, there's enough energy during the growing season to lift it up and create rain, even in these areas of the world that are quite arid. So what we determined is that we have a surface-atmosphere coupling that people have called wet coupled. So the more moisture you get at the surface, the greater likelihood of clouds and rain. This is a slightly complicated figure. So here we have the moisture lapse rate. This is again from Tobias' paper in 2018. You have moisture content, right? So more than often likely stay over here. This is an interquartile range of observations. And so for different levels of the Bowen ratio, if you are above that line, you can have clouds. And if below it, you're probably not going to have convective clouds. So as the surface gets moisture and the Bowen ratio gets lower, recalling again the Bowen ratio is sensible divided by latent heats, it's much more easy under wetter conditions to have cloudiness. And once you get very dry, harder to happen. You need a lot more moisture. And this happens to be reversed during July and August when the atmosphere is dry coupled, and it's a lot of energy is necessary to create big convective clouds during those periods, and rain is exceedingly unlikely. So when you do all this modeling and go through all this work, you see if we have a Bowen ratio of 2 in the 80s and kind of 1 in the present, and we're talking about probabilities of a crossing between the atmospheric boundary layer and the lifted condensation level, you have a 10% increase in rain. This doesn't sound like a lot. Maybe it isn't, across the entire April to September period. If we just focus on those key months of May and June, in the 80s, 70s, 80s, right, especially this drought period in the late 80s, early 90s, we have a more than 40% greater chance of convective precipitation now, using this model and using the inference, during May and June than we did in the past. In fact, now at over half the days, there is a crossing between the lifted condensation level and atmospheric boundary layer, which again is our criterion for saying, can you have a cloud? So, things have gotten much more, convective precipitation now much more likely, and perhaps it's not entirely surprising that at least northeastern Montana, this area around Glasgow, has about triple the rain in May and about double the rain in June than it had in the early 1990s. So the early growing season is now seeing far more moisture. Our argument is that because there's now far more moisture at the surface, now that far more crops are being planted and far less bare ground is around. This is entirely a happy story. There is a lot more flooding now in places like Saskatchewan that we often don't hear about. I don't necessarily argue that this is the mechanism for that, but there is way more water in the Northern Plains now than there used to be. And to wit, okay, this fallow figure that I showed you before, you saw this enormous increase, okay, in fallow in the late 2000s. This is because the fields were too wet to plant. Right? Floods created a pretty dire situation for a lot of Canadian agriculture. At those periods, you see really is hitting Manitoba, Saskatchewan, west of Alberta. But, and this is really the kicker, when you look at changes in groundwater hydrology from the GRACE satellite, this is a paper from Rodell and others in 2018, the Northern Plains here has seen more groundwater increases than almost anywhere in the world, except maybe Angola. Whereas the Southern Plains, okay, of course, there's the very well-known groundwater depletion in India and all sorts of places that are seeing less groundwater, is a hot spot for groundwater depletion. So we have this bipole where the Northern Plains are getting way, way wetter. Just over the past few years, so GRACE started in, when did it start? 2002. This is even a shorter time period. and we have this area, mostly upwind of Wisconsin, seeing extreme differences in the amount of water in the ground, huge differences in precipitation, and eastern Montana, the Dakotas, these places are oftentimes the genesis of where mesoscale convective storms occur. So this is from Sims satellite blog. I took this directly from the web, June 18, 2014. This isn't, of course, therefore, the mesoscale convective system that brought the floods to Madison and Middleton a couple summers ago, but you see, okay, more rain might mean good things for the farmers in dryland cropping regions of Montana. Things are happening downwind, and I would argue that we really need to get a better handle on this because, again, the climate and the hydroclimate of the northern plains is to a large degree our hydroclimate as well. And if you simply scale the Eddy covariance measurements that I presented before from Vicadol 2016, 30 million more cubic meters of water have entered the atmosphere simply because of changing cropping practices in the northern plains. Does that mean that this is what's causing that to happen? Absolutely not. Yes, question.
What fraction of that 30 million cubic meters is irrigated water? Must be a large fraction, right?
No.
No, that's
a
it.
tiny fraction. Here's why. Where's my figure? I'm looking for a good map. There is a little bit of irrigation. It tends to be toward the river valleys. There's irrigation. So Yellowstone River, parts of the Milk River are irrigated. There's a couple of unique geological formations. Irrigation happens here, for the most part. A little irrigation here, okay? But this is mostly dryland agriculture. So, river valleys, yes, absolutely. Lots of irrigation. Everywhere else, not so much. So, it's predominantly dryland ag. But back to the question that motivated me about South Dakota, I think it is the irrigation from Nebraska that's causing that pattern for a number of reasons that I probably shouldn't get into right now. So, back to the matter at hand. Good, very good question. Another thing, and this is a figure that Gabe made that really got me thinking, there's an enormous difference in the timing of precipitation. Okay, so especially back, right, the 50s and 60s, you normally get precipitation events happening in the evening. The dawn layer is kind of starting to collapse right here, and now we're getting much more precipitation earlier in the day. So something is happening, right? Changes are occurring. And the way that we're tackling this problem, of course, is using models. Specifically, the Weather Research and Forecasting model, where Gabe has been very active working with scientists from NCAR to investigate a pretty large area. This has changed slightly in its size, and running the model at a 4-kilometer convective permitting mode, right, to try to formally simulate rather than parameterize convective clouds and convective storms. His mentor there has called this sort of the terra incognita between large eddy simulations and global climate models. So right now we're really trying to get the land surface right to drill down to do entire years of 4-kilometer convective permitting modeling across the central part of North America, including, of course, Canada, and then we have an outer grid of 20 kilometers. To start, Gabe has performed 12-kilometer WRF runs, where you see here, using a land cover map that our colleagues at Wyoming have helped us with, big differences in the 2-meter air temperature. This is in Kelvin, with fallow versus without fallow. So with fallow here is in red, okay, that's the difference. And you see, of course, areas that have a lot of bare ground have a lot more heat through the surface. And I say test because Gabe was monkeying around with the sea surface temperatures, resulting in some vagaries about Lake Winnipeg and Lake Superior, but this is why they're tests. This is not the final run. This is Gabe demonstrating that we're making good progress. And you'll see also quite distinctly that sea surface temperature problem arising here in this precipitation difference map. Now this is using the current MODIS land cover map versus a map of 1984 era fallow. And you can see perhaps some increases in moisture, but again, his initial results are still run at 12 kilometers. And he's just kind of testing, right? This is just with a parameterization scheme for convective precipitation. I couldn't even tell you which one, as a way to get his WRF runs with 4-kilometer land surface and modeling all up to speed. So, if you're a happy little cloud in Montana, you have a lot more friends nowadays than you used to. There are also perhaps more major storms. We're not really studying that. We're just studying the likelihood that you can get atmospheres that look like this versus ones like traditional big sky Montana where you can see as far as you can because there's nothing in your way until that mountain range way in the distance. But we had the worst drought on record in parts of eastern Montana in 2017. Okay, what happened? This was a flash drought. So this is the U.S. Drought Monitor Drought Index. And this is Bismarck, Glasgow, Great Falls, Montana, Rapid City, Wyoming. Progression, where's my counter? Here we go. Starting in March, you see, oh, maybe it'll dry around Rapid City. Who cares? Not that wet. May, still not that wet. Okay, June, oh, it's getting dry. Getting really dry in July. Now all of a sudden, we're in exceptional drought land. In Jordan, Montana, the biggest fire in the U.S. was in eastern Montana that year. And it was the driest in parts of eastern Montana on record. The problem, you saw that genesis of the drought really starting in June, is that NOAA, if you guys know Tanya Franson, she's the NOAA coordinator in Glasgow. She's very active in AMS, and she was against the release of this particular outlook, but this is a negative forecast suggesting wetter than average conditions across large swaths of the Great Plains. You would do better by chance. My 4-year-old would do better in predicting what was going to happen over the next 3 months of the climate of the Northern Plains in 2017. So this flash drought, by definition, it took everyone really by surprise. This is the cumulative sum of precipitation in Bismarck, Rapid City, which again didn't really see the end of that drought, Great Falls, interesting case here, in Glasgow, where spring precipitation was pretty normal. In fact, precipitation in Great Falls, and this is really in the center of a huge agricultural area of Montana, it was greater than normal, such that when the drought occurred, the crops had already been harvested, and it didn't really matter. In Glasgow, the rain just stopped. And they reached extreme drought conditions, widespread crop failures. They're still digging out from that drought a couple years ago. So this is a paper we published in 2018 in Hess, where we looked at that drought and we asked, what is happening? And what we're building up toward with grants that we're still trying to work at is an idea that a flash drought is a breakdown in surface-atmosphere coupling. And because it's a breakdown in surface-atmosphere coupling, there is preceding information that might help us forecast it. So this is a wonderful image by the Paul Diermeyer group at George Mason University. And what he's showing here across the entire globe, I've picked out Glasgow with that X, is when you have a relationship between soil moisture and surface fluxes. Right? So as things get dry, plants begin to wilt and you have less evaporation. That's what's called the terrestrial leg here. There's also a relationship between surface fluxes and the planetary boundary layer. That's what's called the atmospheric leg. And then a complete coupling between soil, surface, and atmosphere. That is happening when this thing turns red. So starting in January, you see, there's not enough energy to have this coupling across the Northern Plains. And as we work into May, okay, right, you already see that turning red, May and June is when you actually already have a complete coupling, in our study region at least, between what's happening with the soil, what's happening with plants, and what's happening with the atmospheric planetary boundary layer. So, is the drought a failure of our expectation that you have a relationship between these aspects of our hydrometeorological system? We are thinking perhaps it might be because there were many clues in the atmosphere that drought was extremely imminent. So what this figure is showing is the CTP high-low framework of Findell and others a number of years ago. This is convective triggering potential. It's similar to CAPE. And this is high-low. This is the difference between the dew points of I forget exactly how high up in the atmosphere, the difference between the dew point and the actual amount of moisture. So this is in degrees Celsius. If you have a value determined above about 20 in this variable called high-low, convective rain is extremely unlikely. And if you're down here, it's likely, but you still need to have convective triggering, enough energy to lift that parcel there up in the first place. So if you're down in this quadrant, right, in March, you don't really have convective precipitation. There still isn't enough energy in the Great Plains for that process to really occur. And then if you have a typical, the 30-year climatology is here with the standard deviation bars, a typical August, right? It doesn't rain in Montana in August. It's just way too dry. So you have not enough moisture in the atmosphere for it to rain. So a typical year, right, you have this period, April, May, June, when there's enough energy and enough moisture for convective events to occur. In 2017, May, and that's that square, that blue square, was drier from the convective triggering potential high-low framework viewpoint than a typical August. So it was less likely to rain in May 2017 when they issued that forecast saying it was going to be wetter than normal, on average, than a typical August in Montana, when it doesn't rain. So there was information in the atmosphere saying that at least part of the precipitation system, namely the convective precipitation system, there's nothing to the synoptic weather, wasn't working right. This is a slightly complicated figure, but let's focus here on Glasgow. This is the cumulative sum of days in which you are not likely to have rain. So this fraction of days is increasing over time as things get drier and drier and drier in Montana. And we were in a zone here in the early growing season in Glasgow where things were already more than one standard deviation above a typical year in terms of lack of likelihood of convective rain. So sorry, this is a little bit of a mental gymnastics here, but once we're way up here, there have already been a number of days when convective rain probably just isn't going to happen, and this already happened, in our case, kind of in early April. All right, so there was a lot of preceding information suggesting that something wasn't working right in the hydrometeorological system of Montana before the drought, leading us to the conclusion that we should incorporate somehow, we don't yet know how, this notion of convective likelihood into drought forecasting. Could this be a way to help us with flash droughts? This is an N=1 drought. This is one flash drought. But the work that we're proposing to do, hopefully with Karen Atkin's help, Karen's very busy right now with this PhD thesis defense. We'd like to get a better handle on if the atmosphere is telling us something about flash droughts before they occur. Right? Because of work that Tobias and others have done, we've seen pretty clearly that there's clues. Is there a signal in all those clues, or are they just happenstance? So where are we at now? Okay, I've discussed these land cover changes and argued that they're important for hydroclimatology. That's not the only thing that happens in the world. We have cold air incursion that happens right, from the Arctic. We have other weather systems, including things like the Pacific Decadal Oscillation, that remain to be understood in terms of how they impact the northern plains. We have a radical increase in the water table. That means there are more small little lakes called prairie potholes. There's just more standing water in the northern plains. It's extremely difficult to get a map of where no-till agriculture has been adopted. It's been adopted across the northern plains. They're no longer tilling up the earth, making for brown dirt anymore. They're leaving the stubble on the surface. This really increases the albedo. This is the leading mechanism for what our colleagues at Zurich, Sonny Seneviratne's lab, argue might be causing the changes. We cannot find a map of where people have moved to no-till or not. Other land use changes, including massive irrigation projects in Nebraska that started in the 70s and 80s, probably ultimately because of that cooling in South Dakota that got me fascinated in the first place. Other aspects of general circulation, a complicated challenge. So, to summarize, we have an enormous area of the land surface, mostly upwind of Wisconsin, that is cooling in May and June, mostly the benefit of agriculture except when there is now more flooding. We have a situation where convective precipitation is coupled to land surface function during the early growing season. More moisture near the surface means that more precipitation is likely. This is beneficial because farmers make money by planting things, not leaving things bare. So they're making money. They're actually conserving soil more by not leaving it bare because it's so windy, it all blows away. And so you kind of have a triple win between rural economics, regional climate to first order, and soil conservation. We also, because we published that paper, of course, has severe droughts. We think that this might have been preceded by a breakdown in an expected land-atmosphere feedback that brings precipitation that farmers rely on, and therefore a coupling of the human climate system during certain times of year in the Great Plains, where agricultural management over enormous areas impacts the atmospheric boundary layer, impacts precipitation processes, impacts ultimately subsequent farmer decisions. We'd like to know more about how strongly that system is coupled, and of course we'd like to know more about how these changes in the northern plains have impacted the Great Lakes regions, including here in Wisconsin. So I was told to be 45 minutes. So I was lucky, and I'm very happy to take any questions.
Definitely time for some questions.
So, do you know if people have studied this drought event and like what was driving the worst this?
Yeah, so there is an enormous blocking pattern that extended from Alaska down to somewhere in the southeast. That was, it was keeping weather systems from moving into the area. Our argument has more to do with the internal cycling of moisture also not working. And of course these things are coupled, right? The land surface isn't the only thing that determines convective precipitation. So there was a large-scale element to that, and we don't know why that blocking ridge was so persistent. There have been a few studies arguing that it was in fact due to anomalously warm sea surface temperature conditions in the North Atlantic, actually. And I can refer you to those papers. So our additional argument for the severity and rapidity of this drought, right? Because in principle, right, we can, at least a few days in advance, watch the synoptic system move across, is that we also, in addition to that precipitation not happening, had a breakdown in surface atmosphere coupling, bringing the little convective storms that are important in dry parts of the world. Does that mean that that's what made it a flash drought? I don't know. I would like to know more. I'd like to know if there were similar things that happened in the famous 2012 drought. I recently heard the argument that the 1988 drought in central U.S. was even worse than that previous drought. So there are a lot of, 1988 drought, I mean. So there are a lot of flash droughts that we now recognize, and we would like to do the detective work to see how much our idea holds water and how much it doesn't. Because I don't expect this to hold all the water. There's more at play. Our argument is that convective precip just wasn't happening, which is interesting, I hope. Question?
Is there anything in the oral tradition of the Sioux or other native tribes that talks about flash droughts?
This is an absolutely fascinating question. I don't know about flash drought. I do know that there's a lot of information in the construct of settlements and where people noted high snow marks. This has to be more than wintertime precipitation. So I've talked with a former student in our department, Lisa Longfight. She's of the Sioux tribe of North Dakota, and I don't know how much traditional knowledge about drought there is. I think that a lot of the traditional knowledge has to do with winter extremes. Probably for good reason. I'd be super interested in knowing if there is more information, because taking this record back further is critical. We're also in an area where there are not a lot of natural lakes or trees to get good paleoclimate records.
Yeah.
So we have a lack of paleoclimate records and perhaps opportunities to learn more from traditional sources. Question?
Yeah, in Colorado, where I've looked a little bit at the summer climate there, Well, it was actually Tarnakey who used to say that the difference between a year of a drought and a year of normal precipitation is one mesoscale convective system. And because it happens so infrequently, when it does, it accounts for a major part of the annual precipitation. One of the things that I studied was mesoscale convective systems in those areas are usually associated with slope flow. And slope flow is usually associated with a confined boundary layer. That if the boundary layer gets too deep and mixes out, you can't establish a slope flow. I'm wondering if that has something to do with it, the fact that these organized mesoscale flow structures, diurnal flow structures, are inhibited in this drought year, and you just don't get that mesoscale convective system, which is going to establish your precipitation.
Long story short, yes, I couldn't agree more, because this is the nice thing about hiring Gabe, because this is fundamentally what he's interested in, and the direction that he's taking this research is using the model to find out how many more mesoscale convective systems the model creates, if that's realistic, the mechanisms behind that. So, lucky for me, Gabe is pushing things in that direction, because I'd like to learn more about, of course, the genesis of MSCs, not really being an expert. I fundamentally do medical variance. So, I know that depending on where you're at, mesoscale convective systems bring, let's say, 30 to 40% of the precipitation. This is work by Carboni. We're friends with his daughter, and this is her husband, Mariah Carboni's dad. So yes, the mesoscale convective systems bring a lot of the precipitation to the plains. If those things aren't around, you're probably in a drought. But where's the chicken and where's the egg? So,
You know that the mesoscale, one of the things is the mesoscale convective systems drop a lot of precipitation, and then that's recycled again and again and again over the period. You miss one of those, you're done.
yeah,
And so even though they may account for 40%, that initial pulse
yeah.
that sets it off may account for most of it.
Yep, and this kind of yo-yoing is something that
Yeah.
I'm particularly fascinated by. And so where that water comes in the first place is really, of course, important too, because it's not all internally recycled.
Yeah.
Just following up on how well constrained are, sorry,
That's okay.
how well constrained are those large scale fluxes in the region in terms of the moisture fluxes? I mean, can you get at the seasonal, the variation, like maybe the annual variation in recycling efficiency based on backing out the moisture fluxes around a certain region?
Our approach, and we don't know if we can do this with current resources, is to do moisture tracking at north. So that being said, it would be nice from the observational perspective to figure out a way of sort of where this water came from, especially thinking about, I mean, this bombshell, which happened, a couple years into our project, that didn't come from internal recycling. That had to come from somewhere. Okay, that's a lot of water. Up to 2 centimeters a year? That's bananas. Over 16 years, that's a lot of water. So, something is happening. There's a question.
Yeah, it's a little bit of change of focus. As a general land service question, so you said the drought of 2017 was the same year we had a lot of big fires in Montana. How much does that change the surface and this kind of interaction, and does it have downstream impacts, or is it too localized to change the next season?
This brings up a really interesting question about where people tend to think about fires in Montana, and to flip all the way back to another slide. Oh, I'm going the wrong way. Sorry, guys. There have been a lot of fires, of course, and a lot of smoke in Montana because of fires in the mountains, the trees. So where's the map? There's the map. And that's what all of this increase in bare ground is fundamentally increases in bark beetle damage, also forest fires, causing the browning. So that fire is there. I would argue that once that fire happened kind of July, August, we're in a time of dry coupling between surface and atmosphere. That would tend to actually slightly increase the chance of precipitation because of the dry coupling, and more sensible heat flux is actually causing more precipitation because of more energy. But I don't know if those fires were quite big enough to have mattered, but it's an interesting question.
I think the seasonality is wrong. Like you say, they're coming in later, not at this.
If it tended to happen early, which is when people for prairie management often burn,
Yeah.
then it might impact things. But again, to me, it's the issue of scale. Once you're talking about the Saskatchewan-sized length scales, all of a sudden these things may happen. I don't know, but for sure, when you have this much bare ground increase in the mountains, something's happening upwind of us. That also goes without saying, but how much, I just don't know. There were more questions, Brad.
So you're using this convective potential on kind of a monthly average basis, and to me,
It's every day.
no, I understand
Every
that
day
you're
or monthly
computing
average.
it every day, but then, to me, that's a much more instantaneous kind of measure. And I'm wondering if that is only working in this area because you're just kind of looking at fair weather cumulus, which kind of happen every day, right?
Well, they kind of happen every day nowadays in the early growing season.
Okay.
They tend to not happen in the late growing season.
But would this be a good, again, I'm thinking of these kind of convective potentials for deep, for intense convection, those are very episodic. I wouldn't think that monthly mean statistics on them would be a predictor, but I'm just wondering whether,
No. We were
because you're
thinking-
looking at just these fair weather cue.
Yeah.
Yeah.
That's kind of our focus. Our focus is just on this boundary layer
Right.
crossing, really. And that I mentioned that earlier in the talk. Like, I would love to understand more of simulating these mesoscale convective systems, simulating all these things, but we're talking about decades and decades of data, and we're just not there with the computational power yet. And you're right. If you look at every day of this is Kirsten Findell's work, which is brilliant, by the way. These all wander quite a bit over the course of a month every day, which is why we were thinking about investigating things in this way. But I mean, we clearly need to do a little bit of work on this to see. And so what's happening? I think there's one more
Let's
question.
take one more and then we can.
Sure.
Go ahead.
So, cool talk. It reminds me of another talk I saw about 2 years ago in Park by High End Tank. What she did was she was coming at it from the exact opposite side as you. She had done a global circulation, global climate model simulation of what's called the circumglobal teleconnection pattern. And you get a big bullseye over the central and northern plains. And then she did something really cool where she modified the interactions with the land. It really changed the circulation pattern, like how much this pattern was activated or not. And I was wondering if you thought any bit about, in these simulations you're about to do, taking a look at the response of the atmospheric circulations, kind of getting out what Steph was talking about,
Yeah.
the other direction.
So this is why I put this kind of center, is the other aspects of the general circulation. I would think that is the best approach. Coming at it, starting from what we do from the micrometeorological perspective, and looking up, this was kind of our initial solution. I would be, one, I want to see that paper.
I'll send it to you.
And two, yeah, I saw a great talk on AMS about this exact sort of thing, where it is really sort of slave to the large scale element of it, but it still begs the question, right? The moisture has to have come from somewhere external, and then how much does it recycle? So we still have this fundamental question of, there's something different happening either during drought or over the past many decades in the Great Plains where we have more moisture that certainly came from somewhere else. And then the follow-on question that is really along more the lines of our expertise is how much of that is, or at least the way we think, I wouldn't say my expertise, is how much of that kind of goes up and down and sort of keeps bringing rain and moves moisture around this somewhat constrained region. But yeah, I'd love to learn more about that. Please send the paper.
All right, with that.
Thanks everyone so much.
That's your person to bother when you can't find me.